Assalamu alaikum dear students. I welcome you to the 21st lecture of probability and stochastic processes. In recent lectures, we have been analyzing the behavior of continuous valued random variables, and in last couple of lectures, we worked with a pair of continuous valued random variables. To analyze their probabilistic behavior, we work with their joint density as well as two marginal densities. While dealing with a pair of random variables, if we want to analyze the behavior of any one of the random variables in the pair, then we only need to work with its marginal density. And if we want to work with both of them, then we need to work with their joint density. We used marginal densities to find probabilities of events which involved only one random variable, and we also found parameters that summarize the behavior of individual random variables, and those parameters were expected value, which is also called mean, and variance, and another related parameter is standard deviation, which is just square root of the variance. If we want to find probabilities of events that involve both of the random variables, then we need to work with the joint density. When dealing with a pair of random variables, we also found some parameters that summarize their joint behavior, particularly their mutual influence of each other or their mutual dependence. Those parameters were correlation, covariance, and correlation coefficient. When we are dealing with a pair of random variables, sometimes we are not interested in the two observed values individually. When there are two random variables and the experiment is performed, we get a length 2 vector, two observations. First observation is the value attained by the first random variable, and the second observation is the value attained by the second random variable. But we are interested in a combination of the two values. So we combine the two values and get a single scalar value, and we are interested in the behavior of that single scalar value. When the two outcomes, two observations, they are random, unpredictable, their combination through a function is also unpredictable. So this scalar valued random variable which we obtain by combining the two observations is also a random variable of scalar type. And this random variable we obtain by combining the two observed values through a function, where function can be any valid function which takes two elements as inputs and gives out one element as outputs. So this function is from R2 to R, from R square to R. It takes vector valued input, two inputs at a time, and gives you a scalar valued output. There are many such functions that we can think of, and they have some practical importance. Let's talk about the example of two televisions that we discussed in previous lecture. So you have purchased two televisions from two different manufacturers. You can call one television as X and other as Y, or more precisely, they are going to fail, and you call the failure time of first television as X, a random variable, and failure time of the second TV as Y, another random variable. Now, you can work with the two observed values, the two failure times, or you can combine them in this way. If you have these two televisions, then you should be interested in that what is the total service time that you obtain. Suppose first TV works for 2 years and second TV works for only 1.5 years. So the total service time is 3.5 years. Even though during the first 1.5 years, both of them were working and during the remaining 6 months only one of them was working. But the total service time that you obtained from these two televisions was 3.5 years. So this is a quantity that we obtain by combining, by simply adding the two service times. So in this case, if X is a random variable measuring the service time or the failure time of first television, Y is the random variable which measures the service time of the second television, then Z or Z, a new random variable, is obtained by taking Z is equal to X plus Y. So this new random variable Z, which we obtained by combining, simply adding the two random variables, is a scalar valued random variable which we are interested in. Why? Because the total service time is important, and while computing the total service time, you are not interested in which TV failed first and which failed second. You are just interested in the total service time, a single quantity obtained from the two quantities that the two televisions generate. So if Z is this random variable, then you might be interested in asking such questions that what is the probability that this Z is less than 2 years, which is something to worry about, that you purchased two televisions and both of them are going to give you a total service time which is less than 2 years. So you want to know what's the probability of that. Similarly, you want to find out what's the probability that total service time is more than 5 years. That is a good thing. But you are not counting on both televisions to work for 2.5 years. You are just thinking that at least one of them should be working at least for 5 years. Or the total service time should be such that when I add the two, it should be at least 5 years. So first TV can fail within first year, but second can fail after fourth year, etc., etc. If you combine the total times and you get more than 5 years, then you are a satisfied customer. Another question would be that what's the probability that the service time is between 2 and 3 years, which is something of satisfactory performance of the two televisions. So this total service time is important derived random variable from the two underlying random variables X and Y. Let's take another example. Suppose there is an aeroplane which has two engines, and this aeroplane can fly safely as long as at least one of the engine is working. So if one engine fails, either left or right, the airplane safely can continue to fly, and it will only be destroyed when both of them are going to fail. So the two engines could be from the same manufacturer or could be from different manufacturers. And if they are different, then they have different failure rates and different probabilistic behavior. If they are same, then most probably they are having the same probabilistic behavior. Their failure rate will be governed by the same underlying probability density function. Now we are interested in a derived random variable Z, which is a function of two random variables X and Y, where X represents the service time of first engine and Y represents the service time of the second engine. If X is going to fail first, then airplane can safely fly on Y, and if Y is going to fail first, then aeroplane is going to safely fly on X. So we want to find out what is the time till then the airplane is safely flying, or the time when at least one of the engines is working. Please note that if one engine has failed, then airplane is going to fly on the remaining engine, and then the failure time or the survival time of the airplane is totally dependent on the probabilistic behavior of the remaining engine. But as long as two engines are working, we have to use the joint density and this derived random variable Z, which depends on X and Y. And this z is obtained from x and y by using this equation. Z is equal to maximum of x and y. We are interested in time, this random quantity, which is the time when both engines fail, or the time till then at least one of the engines is working. So this is the equation. Z is equal to maximum of x and y. So this z is a random quantity, and we want to find the probability density of this random variable. And if we have found such probability density function, then we can ask interesting questions, that what is the probability that for first 6 months of ownership of the aeroplane is going to fly safely. That is, not both of them are going to fail. Or we can ask such questions, that what is the probability that the aeroplane is going to safely fly for at least 12 years. All these kind of questions which involve the safe flight, capacity of the aeroplane to safely fly, depend on at least one engine working. They can be answered by taking the probability density function of this random variable z, which is equal to max of x comma y, and working with this probability density function. Coming back to the example of 2 televisions and the total service time. We have already worked with this total service time when 2 lectures ago we asked this question, that if there are 2 televisions with their own failure rates and their joint density assuming their independence, then what is the probability that the total service time will be less than some value 25 or 30 or 20. We solve this for a particular value of total service time. We did not make the total service time as a random variable. Today we are going to make the total service time as a random variable z, and then we are going to find the probability density function of z, and then work with this probability density function to answer all sort of questions about the total service time of the 2 televisions. As I already mentioned, z in this case is random variable which is obtained from 2 random variables x and y by using equation z is equal to x plus y. Let's take another example. Suppose you pick 2 numbers randomly and both numbers are between 0 and 1. So you pick the 2 numbers, you call the first number x, the second number y, and you get a point in the first quadrant of xy plane as x comma y, where x and y both are between 0 and 1. So this point is going to lie between x belonging to 0 and 1 and y belonging to 0 and 1. So 1 by 1 square in the first quadrant, where one corner is touching the origin. Now this point can lie anywhere, and you can assume an underlying joint probability density of this point. This joint density will be a flat surface if you assume that points are picked independent of each other and they are equally likely to occur between 0 and 1 and 0 and 1. So the joint probability density will be flat in this 1 by 1 square in the first quadrant. Now the question is, what is the distance of this point from the origin? We are not interested in the individual values of x and y, but a combined effect of x and y, which is the distance from origin to this point x comma y. And as you very well know, that this distance is a function of both x and y, and it is given by the formula square root of x square plus y square. So you call this distance z. So this z is a random variable which depends on 2 random variables x and y, which assume values between 0 and 1 and 0 and 1. So this z, which is the distance of the point x comma y from origin, is a new random variable, a scalar valued random variable. And if you think about it, this random variable is going to assume values between 0 and square root of 2. 1.4142 and so on. So this was another simple example of deriving a scalar valued random variable from two underlying random variables. You can combine two random variables using other formulas like z is equal to x plus y, x minus y, max of x comma y, min of x comma y, x multiplied by y, x divided by y, y divided by x, or square root of x square plus y square. You can think of any function, combine the two observations of random variable x and y, using that function get the value of z, and then you talk about the probability density function of z so that you can answer interesting questions regarding this z. We are going to start our analysis of such problems with our example of two television sets, and we are going to work with the total service time as an example of a derived random variable from two underlying random variables. So we have already found probability of one event which involved total service time, and we found that to find the probability of an event like this, that total service time is less than 20 months, we have to find the volume of the sand hill representing the joint probability density in such a way that all the points in this sample space are included in this probability determination, which give us a total service time of less than the value we are interested in. So if we fix the value at 20, we have to include all the pairs x comma y such that x plus y is less than 20. We have to include 5 comma 5, 10 comma 5, even 10 comma 10, 15 comma 5 and 0 comma 20, but we cannot include 20 comma 20. So all the points which give a sum of less than 20 are going to be included. So where they are in a triangle which is bounded from below by the x-axis, from the left side by the y-axis, and then diagonally by a line which is x plus y is equal to 20. 20 is the value which we are interested in, and we are interested in all those pairs of points such that x plus y is less than 20. So if we take this equation that x plus y is less than 20 and take x to the other side, we have y is less than 20 minus x. So y is less than 20 minus x represent all the points below this line. Y is equal to 20 minus x. So y is equal to 20 minus x passes the y-axis as 20, the intercept, and it has a slope of minus 1. So it has an angle of 135 degrees with respect to x-axis. So it's a diagonal line with an orientation of 135. It passes through point 0, 20 and 20, 0, and it's diagonal with 135 degree orientation. So if you find the volume of the sand hill in this triangular region, you find your probability of total service time being less than 20. But if you are interested in finding all possible values of service times and their probabilities, then you have to vary this value z. Z will not be fixed at 20, it will start from a lower value and it will go on higher value. And as you take higher values of z, you will take more and more mass of this sand hill into the probability computation. And if you are computing such probabilities for events like the total service time is less than equal to a small number z, where z takes on values from 0 to infinity, you are computing cumulative density function or CDF. So by varying this parameter z, the small z, from 0 to infinity, and as you vary, you take probability of z, which is x plus y, being less than the value of z, then you are taking integration of bigger and bigger and bigger triangles. As you can see on the slide, I have drawn a few diagonal lines at z is equal to 5, z is equal to 10, z is equal to 20, z is equal to 40, and z is equal to 60. These lines represent bigger and bigger triangles which are going to contribute towards the probabilities of events like the total service time is less than 5, less than 10, less than 20, less than 40, and less than 60. Even though the line at z is equal to 60 is not making the region triangular, but it is triangular. Remember, we have only shown the joint density in a 40 by 40 square. Actually, this joint density is defined for the whole first quadrant. So this is indeed a big triangle, and its volume contribution is going to be more than the volume contribution of the line drawn at 40. So if z is our parameter and we want to find the probability of total service time being less than z, then you have to find the volume of the sand hill, which is bounded by x-axis, y-axis, and a diagonal line joining z, 0 and 0, z. So when this joint density, which is a function of x and y, is going to be integrated with respect to x and with respect to y using a double integral, but one of the boundary is a function of z, a line from z, 0 to 0, z, the answer is going to be a function of z. That is exactly what we want. This function of z will be the CDF of random variable z. And if you have the CDF, you can certainly find the PDF, the probability density function, by differentiating this CDF, which is a function of z, with respect to z. And once you have the PDF of this random variable, you can find probabilities of all the interesting events that you are interested in. Let's see how this double integral is going to formulate it. If you see on your screen, in this slide, you can see that the first quadrant is bounded from below by the x-axis, from left by the y-axis, and from the right by the diagonal line which passes through z, 0 on the x-axis and 0, z on the y-axis. You want to find the volume under this triangular region, then you have to find a double integral, but the limits of double integral are going to be functions of z. As you can see in the slide, this double integral is implemented by a repeated integral of thin slices of the volume, where these slices are horizontal. They start from y-axis and end at the diagonal line, and these slices are taken from y is equal to 0 all the way to y is equal to z. So when you are taking volume of a thin slice closer to the x-axis, the length of the slice is longer, and when you are taking volume under a slice which is closer to point 0, z, the length of the slice is smaller. So you take volumes of all these slices and you get the value of your double integral. The next slide shows you the actual expressions used in this integral. As you can see, the outer integral is with respect to y. So the inner integral is with respect to x, because you are taking a slice horizontally. So when you are taking the volume of sand hill under the slice, then you are integrating with respect to x with a constant value of y. Once this integral is evaluated, you move to the next slice, and this movement is along y. So outer integral is with respect to y and inner integral is with respect to x. The limits on the inner integral start from 0, the left side, which is the y-axis, and end at a point which is z minus y. So it depends where your slice is. If slice is very low, say y is a smaller number, then z minus y, the length of the slice is large. And if the value of y is large, the z minus y, the length of the slice is small. Hence, the limits on integral start from 0 and end at z minus y. And as you can see on the slide, the outer integral with respect to y, which sums up the volumes of all these slices, starts from 0 and ends at z. In this double integral, because of the independence of two random variables x and y, we can separate the joint density into two functions, and the function which is not dependent on x can be brought outside the integral of x. Hence, in the next line you see that I have taken the constant 0.005 outside, and then there is the integral with respect to y, which includes e raised to power minus y over 20, and then inside there is an integral with respect to x, which starts from 0, ends at z minus y, and it only integrates the part which involves x, that is e raised to power minus x over 10. If you evaluate this repeated iterated integral, you get fz, which is cumulative density function of new random variable z, and it comes out to be 1 minus 2 e raised to power minus z over 20 plus e raised to power minus z over 10. We can take many values of z ranging from 0 to a large value and plot this CDF, and you can see this plot on your screen. This plot looks like the CDF of exponential random variable, but there is a difference. I hope you can see that in exponential random variable, when the CDF starts at 0, it rises with a sharp slope, with a high value of slope. It rises sharply. But in this case, for this random variable z, the slope initially is very small. Actually, it's 0. It rises, the slope increases, it rises, and after a certain point, it flattens out, and then the rate of increase of this CDF is again small. So the rate of increase of CDF, which is the value of PDF, is initially small, then a large value, and then it again becomes small. That's a hint for guessing the shape of the PDF of this new random variable. And if you take the CDF, differentiate it, you can get the expression of PDF, and that expression is e raised to power minus z over 20 minus e raised to power minus z over 10 whole divided by 10. You can see this expression on the screen as well as the plot of the PDF. This expression is interesting, and you should observe that it looks like the difference of two exponential PDFs with one difference. If it was a difference of two exponential PDFs, then you should see a constant of 1 over 20 next to e raised to power minus z over 20, and a constant of 1 over 10 next to e raised to power minus z over 10. But this normalizing constant is same for those two parts. So it is 1 over 10 times e raised to power minus z over 20 minus 1 over 10 times e raised to power minus z over 10. So at z is equal to 0, these two expressions without 1 over 10 are 1, and with the common 1 over 10 normalizing factor, they cancel each other, and the PDF starts at 0. Unlike exponential distributions where PDF starts at a higher value, for this random variable z, which is modeling the total service time of two televisions, where each television has a service time modeled with exponential distribution, has a PDF which starts at 0, goes to a high value, and then it comes down again. You can use this PDF to answer interesting questions regarding the total service time of the two televisions that you are working with. For example, we can ask this question, that what is the probability that total service time will be between 2 and 3 years, between 24 and 36 months, or what is the probability that total service time will be more than 60 months or 5 years. Probabilities of these two events will be determined by taking the area under this curve using appropriate limits. For example, for the first question, where we want to find the probability of service time being between 24 and 36 months, the integration will be from x, or in this case z, belonging to 24 to 36, and you will take the area under the curve. This is shown on your screen in red color, and this red color region represents the area under curve where z is bounded from the left by number 24 and from the right by number 36, and from the top by the PDF we just derived. And when you work these things out, it comes out that probability of this event is 0.208. So there is a probability of 20.8% that your two televisions will give you a total service time that will lie somewhere between 2 and 3 years. The other event where the total service time is going to be more than 5 years or more than 60 months is shown on your screen in green, and this represents the total area under the PDF to the right of point 60. To find this probability, you will take integration of this PDF from 60 to positive infinity. I have only shown the z values to 120 months, but you can take additional values even though the PDF has come down to be a very small value for z values larger than 120. If you evaluate this integral properly, this integral comes out to be 0.097. So probability of your two televisions giving you a total service time of more than 5 years is less than 10%. It is 9.7%. So probability is reasonable, around 20%, that the two televisions will give you a total service time of something between 2 and 3 years, and probability is relatively small, less than 10%, that they will give you a total service time of more than 5 years. So by combining the two observations and making a new random variable and working with the PDF of this new random variable, we can quickly answer questions that interest us. In this case, the questions related to the total service time of two televisions which follow their own failure patterns, and they have their joint density which is obtained by multiplying the two individual densities under the assumption that the two televisions fail independent of each other. You can certainly ask other interesting questions about the behavior of two televisions by forming a derived random variable using a different function. We just finished the derivation of PDF and CDF of a derived random variable z, which was obtained by using the formula z is equal to x plus y. Instead of using x plus y, let's use y minus x. So our random variable z is y minus x. And what does it signify? You know the two televisions are going to fail independent of each other, and it's possible that x fails first and y fails later, or the other way around, that y fails first and x fails later. If they fail at the same time, fine, but the probability of those events is going to be 0, because those events are represented by a line, and in continuous random variables we only assign probabilities to events which are represented by finite area on the joint probability space. When you are working with a derived random variable z is equal to y minus x, you are interested in the difference between the service times of two televisions. Y is the service time of the television Y, and x is a random variable representing the service time of other television X. So when you take y minus x, you are interested in the difference between the failure times of the two televisions. And you can ask interesting questions like this, that what is the probability that television Y is going to fail 2 years or more later than the failure of television X, or other way around, that what's the probability that television X is going to fail later after television Y by a margin of at least 2 years. So if you are interested in questions like this, then you have to find the PDF of this new derived random variable z, where z is y minus x. Let's try to remember what the marginal density of x and y were. We started with marginal density of x to be 0.1 into e raised to power minus x over 10. And marginal density of y was 0.05 e raised to power minus y over 20. We plotted these probability density functions in a lecture which was, I think, 12th or 13th lecture, and we analyzed their behavior, and we found that television Y with a lambda of 20 was more reliable, and television X with a lambda of 10 was less reliable. So when you ask a question like this, what is the probability that Y is going to fail later with a margin of at least 2 years? Being more reliable, Y has more probability of failing later by this much margin. So this probability is going to be more than the probability of X failing later than Y with a margin of 2 years or more. We will find these probabilities in a while, but first we have to find the PDF and CDF of this random variable z, which is y minus x. Let's find out this probability through CDF. What is CDF? It is cumulative density function. It is a parameterized probability value, and it is the probability of z being less than the value of the parameter small z. So we are going to find probabilities of events like z is less than or equal to small parameter value z, where z, the small z, is going to take values over its specified range. Since we are taking y minus x, the difference between the two service times, it is possible that x is larger than y, so y minus x is going to give us a negative number. So the range of this random variable z is a real value starting from a very large negative value and ending at a very large positive value. So our range is from minus infinity to infinity, theoretically speaking. So we are going to find the CDF and PDF for this random variable z, which attains its values from minus infinity to infinity. And we are going to do that by taking the integration of the sand hill representing the joint density of x and y in appropriate manner, and this integration will be for the region which is controlled by the value of this parameter z. So how this is going to control it? It is not difficult to see, because the random variable z is y minus x. When we are trying to find probability of this random variable z being less than equal to a certain value of parameter small z, then we are trying to find the probability of y minus x being less than this parameter z. So if y takes on a value small y and random variable x takes on a value of small x, then y minus x should be less than or equal to this small z. So when you rearrange the term, you are interested in finding probabilities of all those points where y minus x is less than z, and if you move x to the other side, y is less than x plus z. Remember, z is a variable parameter. So this is a straight line, y is equal to x plus z, where z is the y-intercept and x, being with coefficient 1, has a slope of 1. So this is a line which is oriented with an angle of 45 degrees, and it changes its y-intercept as the value of the parameter z changes. On your screen, you can see these lines for 5 different values of y-intercept, which is z, and these lines are drawn for y-intercept values of minus 25, minus 10, 0, 10, and 25. For a certain value of y-intercept, which is z, the parameter we are changing, the region of the joint density which is going to contribute towards the probability of the event z being less than that parameter is decided by the value of this z. If you see on the next slide, you see how this formulation works. In this slide, which is valid for negative intercept values, we see that the region which is going to be integrated to find the total volume of the sandhill is bounded from below by the x-axis and from above by this line y is equal to z plus x or x plus z. Remember, z is a negative number, so y-intercept is in the lower region for a negative value of y, which makes this region a triangular shaped region where the integration is bounded from below by x-axis and from above by this line, but the point where this line and x-axis meet is to the right of origin. Origin is not included. So the double integral for this case is evaluated as a sequence of volumes of thin vertical slices, and the integration of vertical slice is with respect to y, and this y starts from 0 and ends at z plus x, and the integration along x, which sums all these volumes of thin slices, starts at minus z and goes all the way to infinity. You can see this formulation on the slide, and this just shows that if you have a z which is negative, you are trying to find probabilities of events like capital Z, the new random variable, being less than or equal to a small number z, and this small number z is a negative number, then the double integration with outer integration with respect to x goes from minus z to infinity, and inner integration with respect to y, the integration of the vertical slice, goes from 0 to z plus x. Once again, due to independence of the two random variables x and y, you can separate the joint PDF and the integration can be easily computed, and it comes out to be 1 over 3 e raised to power plus z over 10. There is a difference. Now, for negative values of z, the CDF has expression 1 over 3 e raised to power plus z over 10. When this parameter z has a positive value or y-intercept is for a positive number, then the region of integration is different. The region is shown in the slide, and you can see that in this case the vertical slice starts from 0 and ends at the same expression z plus x, but the integration with respect to x is always starting from 0 and going to infinity. So for positive values of this intercept, the integration, the double integral, comes out to be an inner integral with respect to y, which starts from 0 and ends at z plus x, the vertical slice, and an outer integral with respect to x, which always starts from 0 and ends at infinity. And by separating the two density functions, you can evaluate this integral, and this comes out to be fz, the CDF of z for positive values of z has an expression of 1 minus 2 over 3 e raised to power minus z over 20. One thing you should always note that for a z value of 0, the value of the first expression of CDF, 1 over 3 e raised to power plus z over 10 is 1 over 3. And for this new expression for positive values, which is 1 minus 2 over 3 e raised to power minus z over 20, is also 1 over 3. So if you combine the two expressions, that is, you use first expression if value of z is negative, and you use second expression if value of z is positive, you will have a CDF which is given by first expression for z values from minus infinity to 0, and from 0 to plus infinity you will have the second expression shown on your screen. The combined effect is a CDF which starts at 0 and reaches to a value of 1. This CDF is plotted on your screen, and you can see that this CDF is a smoothly varying, starts from a low value and rises slowly, and when we approach a value of minus 10 or minus 5, it rises sharply, and then it again tapers off and slowly increases to a final asymptotic value of 1, as all CDFs do. It's very easy to find the PDF of this random variable. You have to use two separate expressions, differentiate them, and you will get two expressions for PDF. One expression will be valid for values of z which are negative, and the other expression will be valid for values of z which are positive. These expressions are shown on the slide, and the PDF is also plotted on your slide. For negative values of z, the PDF comes out to be 1 over 30 times e raised to power plus z over 10. And for positive values of z, this comes out to be 1 over 30 e raised to power minus z over 20. And for value of z which is exactly equal to 0, this comes out to be 1 over 30. So this PDF is given by one expression for negative values of z, which start at a small value, goes up to 1 over 30, and from that point onward it is given by the second expression which is shown on your screen, and then it again goes down, and the peak value of this PDF is at 0, but this peak is not smooth, it is like a corner, and the tip of the corner is at a height of 1 over 30. We can certainly find probabilities of interesting events for this PDF for the derived random variable z, which is y minus x. And the two interesting events are that what's the probability that x, the less reliable one, beats the more reliable TV by a margin of 20 months. And the other event is what's the probability of the y, more reliable TV, beating the less reliable x by a margin of more than 20. To find answers for these questions, all you need to do is work with this PDF and find the areas under the PDF using appropriate limits. This has been done, and you can see the results on slide, which shows in red color the region which contributes to the event, which is represented by x being larger than y, with a margin of 20. So x is larger than y minus x is a negative number, and this is more negative than minus 20, meaning x is going to beat y by a margin of 20 months or more. And in green color, you see the probability of the event that y is going to beat x with a margin of at least 20 months. If you work out the PDF of this random variable z and find the probabilities of these two events, they come out to be 4.5% for the event shown in red and 24.5% for the event shown in green. So there is only 4.5% chance that less reliable x is going to beat the more reliable y by a margin of 20 months. But probability of this happening in the reverse order, that is y, the more reliable one, beating x, the less reliable one, with a margin of 20 months or more, is 24.5. So there is a chance of 24.5% that more reliable will beat the less reliable by a margin of 20 months or more. The answers are as we expect them to be from the common sense. But by working with the underlying sample space and the joint probability density function and the derived random variable and the PDF of the derived random variable, and then finding the probabilities of these events, is a more robust and proper way to analyze the probabilistic events. Today we started our analysis of derived scalar valued random variables, which are a function of two underlying random variables. Such a derived random variable is important because it summarizes the interesting behavior of two underlying random variables. We took the example of two televisions, and assuming that they fail independently, we answered interesting questions about the total service time and the difference between the service times of the two televisions. We'll continue with our discussion of these derived random variables from the next lecture. Until then, I wish you the best. Thank you. Khuda Hafiz.